Hello guys, in this video we are doing organic chemistry and we want to see alkanes. So known to be saturated hydrocarbons. This means it consists of single bond between carbon atoms. It's like this. These are two carbon atoms, so we have single bonds. We don't have any carbon atoms that have double bond. So that's the meaning of the word saturated hydrocarbons. Then their functional group. Their functional group is alkyl. Alkyl is this group. That's what we call alkyl, made up of single bonds between carbon atoms. Then the general formula for alkanes is CN H2N plus 2. So this means if we have one carbon, the formula that we'll get is CH, then 2 times 1, which is a 2 plus 2, then 4. So our alkane will be CH4. If we have two carbons, it's C2H, 2 times 2, then we get a 4 plus 2, which is equal to 6. So C2H6. Names of alkanes, they end with the suffix ANE. So let's see how we name alkanes according to number of carbons. Carbon, it falls under meth group, which is methane. If we have two carbons, it falls under eth group, which is ethane. If we have three, it falls under prop, which is propane. Then 4, it falls under bute, which is butane. Then 5 falls under pent, which is pentane. Then 6 falls under hex, which is hexane. Then 7 falls under hept, then we get heptane. Then 8 falls under oct, then it gives us octane. This is what we call structural formula. The molecular formula. Molecular formula just shows the actual number of carbons. So we have 4 carbons. Then hydrogens, we count hydrogens in total. It gives us 10. We get 10 hydrogens. So this is C4H10. That's our molecular formula. Then we also have what is called condensed structural formula. It shows the correct arrangement of atoms in a molecule. So we have carbon. This first carbon is surrounded by 1, 2, 3 hydrogens. So it's CH3. Then we have this carbon, you have 2 hydrogens. Then we have EH2. Then we go to the next one, it's CH2 again. Then lastly, it is CH3. That's our. Then we might have the branched chain alkanes and the straight chain alkanes. So if we have a branched chain like this, our IUPAC name will be 2-methyl. Then we check our main chain, how many carbons are there? We have 1, 2, 3. 3 falls under prop, which is propane. So our IUPAC name is 2-methyl propane. Maximum number of carbon is 7. We have 7, which is the straight one, which is like this. Then we have these ones, it's our branches, and this one. So now we want to number our carbons. So the rule that you can use when numbering your carbons, you start from the carbon that is closer to the branched chain. I mean the outer carbons, something like this. You can see this carbon is closer to the branch. Unlike this one, you have one carbon in between for you to reach the branched chain. So we can take the closest one, which is this one. So we'll number it number 1, number 2, number 3, number 4, 5, 6, 7. So it's 2,3-dimethyl-heptane. The physical properties of alkanes. Intermolecular forces present in alkanes are weak London forces. Really have a lower boiling point due to its weak London forces. This is the reason why alkanes have lower boiling point. This is due to weaker intermolecular forces in brackets London forces that require energy to overcome. Physical properties of long chain alkanes and short chain alkanes. Generally, the boiling point of alkanes increases as the number of carbon atom increases. This means the more the carbon atoms, or the higher the boiling point increases. Then we have what is called vapor pressure. Vapor pressure is a pressure exerted by a liquid that is boiling. So vapor pressure opposes the boiling point. So boiling point increases from methane to octane. Then vapor pressure increases from octane to methane. This is trend in boiling points and vapor pressure of alkanes. This is a question. For you to answer this type of question, you need to mention the type of intermolecular forces present in the compound. You also have to mention molecular size is also important in this question. So you say C8H18 has a bigger molecular size. Since you have bigger molecular size, then it means you have a larger surface area of intermolecular forces. Once we have a large surface area, then we have a strong intermolecular forces because we have more points of contact of intermolecular forces. In this case, we are talking of London forces. Hence, more energy is required to overcome the intermolecular forces, which are London forces in C8H18 than CH4.